Good morning, all. Am I audible? And can you see the slide I shared? Okay. Uh, Anybody from batch B? Okay. Okay. Fine. So actually, I expect students from both divisions. 60. Join. We'll just wait for 1 more minute and we'll start immediately. I just posted. Last 10 seconds. Can you see? Okay. Now this is the answer. So 5 is the or currently 40% students are able to give answer, I guess. Reason I don't know. Still 14% students are there. They have selected A. 4, no. So new you need to count. Terminated you need to count. ready, running, and waiting. 3 plus 2, 5. So we already finished this part yesterday. Now let us move next. Now the information of a specific needs to be stored somewhere, and that part is called the process control block, PCB in short. Okay. So PCB is hold. Sneha Patil, mute yourself. Okay. So PCB is used to store the information associated with each process. And this PCB is also called as task control block. So fine. Now what kind of information is stored in PCB? Okay. So number one, PCB holds information about what is the current state of the process. And current state of process, we are already aware there are 5 states. Okay. So that state information will be stored, whether it is just newly created process or ready or running or waiting, suspended, terminated, in which state the process is there. So that is the process state. Very first kind of information. Next one is the program counter. Okay. Most of the time I have an example for this program counter, which holds the address of next instruction to execute. In our program, we have like first instruction, second instruction, third instruction, fourth instruction. Now that is all logical addresses. But when it comes to actual execution of instruction from memory, our logical address is located somewhere. Okay, and that has to be loaded into the program counter so that processor will come to know what is the address of next instruction to execute. So that is the program counter. Fine. So this is PC program counter. Now one more thing is there, process number. This process number, so each and every process is uniquely identified by unsigned integer. So it is non-negative number, and that is the process number. This is also called as the PID. So let me write it here, PID. Process number is nothing but PID. Okay. So this one. Fine. So process. So very clear is that is process identification number, or just process number for simple thing. In which state my process is currently there, that is the state of the process. Then program counter. associated with that process, what is the next instruction to execute. Now, why we need to keep this information is, if you are switching from one process to other process, then definitely whenever you are coming back to your process, the thing is you should be able to continue from where you have stopped. And that purpose is solved by program counter. Fine. Next is different CPU registers are there. Vaishnavi, mute yourself. Okay. So different CPU registers are there. Maybe all are not used by that process, but whatever the registers of CPU used by that process, so process centric registers, so whatever the values of that, you imagine something like you are doing some sort of addition, and you loaded say first operand into the accumulator, and before loading second operand somewhere in other register, because your time quantum is, you switch from one process to other process. Now whenever you are coming back, maybe you will continue with the addition, like loading the second operand, but what happens to first operand? That also has to store somewhere, and that is the reason the CPU registers are stored somewhere, and the location for that is PCB, process control block. Okay, so CPU registers are there. CPU scheduling information is also there. Like for example, what is priority of this process, then where it is actually in the scheduling queue. Imagine you have the round robin algorithm, say 5 processes are there, then what happens in round robin is process P1 executed for some time, then P2, then P3, then P4, then P5, then P1, P2, P3, P4, P5, something like this. Now suppose P2 is finished, so P1, P3, P4, P5, P1, it is something like that. So you need to keep track in the scheduling queue by means of pointers. Okay, so that is one more thing. Next is the memory management information, especially memory limit. Memory limit is where your process starts in the memory and where it finishes, so that your process will not be allowed to access anything else outside of your region in the memory. So that memory management related information is also available. Next is accounting information, wherein I already mentioned what is the accounting. Whatever the resources of operating systems are there, which resource is utilized by what process and for how long, or maybe in percentage, how much percent of that resource is used, or maybe in terms of time, for how long that resource is used. So this kind of information, that is the accounting information, is also stored process control block, which includes like the CPU time, then clock time elapsed since start, then what are different time limits for that process. Okay, and next one is the IO status information. One of the IO required is list of, say for example, open files. So whatever the input output devices that are assigned to your process. Okay, so later we'll come to know that whenever you start any process, by default 3 files are attached to you, your process, and these files are the standard input file, standard output file, and standard error file. So whatever the list of open files are there, that is also stored. And anyways, files are stored, that means just descriptors are stored there, file descriptors, and that is just an integer. So for example, 0, when you say 0, it is the standard input, 1 is standard output, 2 is standard error, something like that. So if you open one more file, yes, file descriptor of that will be also stored here. So most of this information, even though seems huge, but they are just kind of integers or pointers where actual information is stored somewhere, and PCB is used to keep track of that. Okay. Fine. So let us move. Do you have any question on this? Process control block. This is one of the important resource allocated to your process when process is created. So that is PCB, also called as a task control block, but PCB is more popular than task control block. So let us call it as a PCB. Okay. Now this is the context switching, you call it as, or CPU switch, whenever you are switching from one process to other process. Now this is actually very simple thing. Assume that there are two processes, process P0, which is mentioned here, process P1, and now CPU want to switch from P0 to P1 and coming back to P0. So actually two context switches are there, two CPU switches are there. So assume your time is in this direction. So this is the time in this direction. At this particular time, process P0 is executing. Now when I say process P0 is executing, what is state of that process? Anybody? Can you put it on chat? At this particular time, if process P0 is executing, exactly correct, that means it is running. Okay, it is running. Fine. And process P1, can you tell me what is the state of process P1? Yes, put your answer on chart. Right. It is Tanuja Sonavle. You can put answer. Don't give the answers on private chat. Send it to everyone. Okay. Now ready is the correct answer. Somebody is also mentioning it is waiting. No, it is not waiting. Waiting is required when that process is waiting for some event to happen. Maybe it is ready there. Okay, maybe it is ready, and because only process which will move to running state is from the ready state only. So that means process P1 should be in the ready. Okay, so at this particular time, as I mentioned, P0 is executing, that means it is running state, and P1 is ready waiting for the processor. Now the next thing is, let us assume at this particular time here somewhere, okay, interrupt occurs, and maybe this is a software interrupt, or maybe system call, whatever, for whatever is the reason. Okay, for whatever the reason, now P0 is now, we need to switch from P0 to P1. Fine. Now what is this interrupt? Let me again explain this part. What is this interrupt? Suppose whatever the CPU time quantum assigned to P0 is finished, and operating system has to select next process, then P0 has to be interrupted. Got it? So reason could be anything. Maybe P0 executing scanf and it is waiting for some sort of input output. Maybe input. Scanf is input thing. Then we need to switch from process P0 to P1. So for whatever the reason, whenever we want to switch from P0 to P1, very first step is save the state information into PCB of 0, where PCB of this 0 denotes the process number. Let us call that as a PID. So PID of this is 0, PID of this process is 1. So save the state into PCB. And not just process state, whatever other parts are there, program counter is there. So whatever we discussed in the previous slide, all that stuff. CPU registers are there, timers are there, accounting information may be updated, all that stuff. So save the state of that process into PCB 0. That will take some time, denoted by ... And then next thing is, now remember, this is done by operating system. So whatever is actually happening here, this is for P0 process. Here, this is for P1 process. And here is at a operating system level. Now, OS will reload the state from PCB1. And in between this, your scheduler starts here. Scheduler selects the next process. I assume that there is process P1 which is selected by scheduler in this time. Then operating system will reload the state from PCB1 because process control block for this process has to be loaded. And during this time, whenever this thing is happening, note that P0 is also idle, not executing. P1 is also idle, that is not executing. Once you reload the state for P1, now here at this place, P1 starts execution. P1 starts execution. Okay. Now, maybe again interrupt occurs or maybe system call is there. Maybe for whatever reason now operating system has to switch from P1 to some other. Exactly same steps will be carried out. So, for example, P1 is currently executing. In order to select P0, save the state of process P1. So in the PCB1, maybe scheduler will be executing here. It will select next process at P0, reload the state of P0, and P0 will continue executing from where it has stopped. So some part is executed here, some part is executed here. I think there is something on chat. Let me check it. Okay. The question is how much memory is assigned to PCB? Is that fixed or dynamic? Definitely it is fixed. Process control block, it is fixed because there are always some upper limits for each and everything. And to make calculations fast, depending upon the operating system, PCBs, for example, there is a list of files. You may wonder, now list of files, how many files? So there is a maximum limit. Say, for example, if a process can open up to say 64 files, then 64 pointers will be there, or 64 integers are required there. So to make it a quick, PCB needs to be fixed because anyways the CPU registers are fixed. Here, let me go back. See here, PID, it is just integer. Program counter, it is just integer. State just could be denoted by even single byte. Okay. Registers, they are fixed. Memory limits, how much memory is there. So this is also fixed. List of open files, that will be there. So 10 files are there. Okay, fine. We'll just use 10 integers there. 50 files are there. I'll use 50 integers. So even though you may feel this is changing dynamic. It is not, because there is upper limit. So those many integers will be there. So because all the parts are almost fixed, PCB is also fixed. Okay. Any doubt in this? So in very simple words, whenever you want to switch from one process to other process, fine. When I want to switch from PI to PJ, then save state information into PCBI. Scheduler will start. It will select the next process, for example, say PJ. Then operating system will reload the state from the process control block of process J. So that is PCB of J. And once it is loaded, then it is not just scheduler and dispatcher. Once the state is loaded, the control will be dispatched to process P1 and now, PJ, and PJ will continue executing. So that is the simplest method in which we switch from one process to other process. Okay. There is question, how many PCBs are there in the OS? It actually depends on the hardware architecture also and the type of operating system also. Reason behind that is very simple. PCBs are stored in memory, and usually PCBs are linked with each other making use of linked list data structure. So whatever different queues are there in the operating system, there are maybe somewhere in this unit we need to see the different queues also. But the question is, how many PCBs are there? It depends on how many maximum processes will be handled by that operating system. Maximum number of processes at a time. And definitely this number is high. If you think of operating who is actually running some sort of, say, web server, imagine CentOS, that is community enterprise operating system used to host the web server, and thousands of requests are coming there. Just for that, what I can say, web server process, just for that web server, so many worker processes are there. And that is in terms of hundreds. So if for single service that much is supported, anyway CentOS is the enterprise operating system, so it is designed for the server, so definitely it can handle multiple processes simultaneously, provided we have that much resources, right? So number of PCBs, for each and every process we need one PCB. Okay, and if all the PCBs are finished, whatever X, that is the maximum limit, after that you cannot create a process. Okay, that is the case. Even though your processes are suspended, no. So definitely there is a limit for that. Now, if you are asking count, don't know. It depends on different architecture of different operating systems. Now, next is threads. There is one more question. Is Arduino a PCB, and if no, then what is difference between them? See, name could be used differently. Like as I mentioned, task control block is there, or maybe multi-threaded operating systems are there also there. But the thing is, each and every operating system has to keep track on processes by means of PCBs. So Arduino should also have process control block. Anyways, these data structures are handled by the core part of your operating system, which is used for process management, and most of the part is not visible to the end users. So that is available in the kernel. Anyways, you can, like if you go with Linux operating system, you will have access to what are different fields in that. Okay, so Arduino also has to provide a kind of PCB where state of process will be stored. Okay, if there is a single operating system, then and then only PCBs are not required. But whenever more than one processes are supported, definitely we need to have PCB. Okay. Now next part is the threads. Now there is something called as a process and there is something called as a thread. Okay. Now processes by default has a single thread of execution. So now we need to understand the difference between the process and thread. Rather than saying difference between process and thread, we need to understand the basics of process, basics of thread. Okay. Now, even though I have a single application, let me give a very simple example. Suppose you are preparing some sort of document making use of any word processor. You think of Microsoft Word, doesn't matter. So Microsoft Word you are typing there, say for example, right? Now, if you do some typing mistake there, what happens is some red underline is appearing below that word. Number one. Number two, if the sentence is wrong grammatically, maybe blue or green line is displayed there. If you type something like TEH, that will be automatically converted to THE. Okay. Now, if you make use of tab and press enter, automatically it will switch to bulleted mode. Right. Now, so many things are happening simultaneously there. Does it mean multiple processes are there? Definitely not. When you are executing that Word application, Microsoft Word application, by default, one thread is there which is accepting your input. Okay, so whatever you are typing, so that will be taken from keyboard to buffers to the application. Anyways, operating system plays vital role there also. Now that application will get the keystroke. Now it has the state information, I can say, not process state, but state information related to like whether the boldface is enabled or not. If it is enabled, whatever the text appearing in front of you will be in the boldface only. And if you make any spelling mistake there, automatically it will what I can say, underline it with red line. Now all these stuffs are happening simultaneously, parallelly. Okay? And that is called as multiple threads of execution. Even though application is single, different parts are running simultaneously. And that is so by default, even though we say processes have single thread of execution, that is multiple program counters per process, and that is to be with the threads. Okay, and this multiple thread of control, in short, they are called as threads. One of the definition for thread is it is lightweight process. Lightweight. When I say lightweight, reason behind that is very simple. It don't require those many resources as a process. Rather than saying don't require, actually it shares the resources of the process. Just what is not shared is the program counter. Otherwise, it will share something like whatever the memory is there, maybe text region is there, data region is there. Okay, whatever your variables you have declared. So that memory part is by default shared with thread, and because of this sharing, separate block is not required. Okay. So, anyways, threading we discuss in more detail later. So this is what this one. When you have multiple threads for your application, anyways, we are going to see how to create a thread, how to run. Maybe we can utilize any of the programming language for that, because threads are almost supported by most of the modern operating systems. They maybe names are different. For example, if you see the C and C++, there are POSIX threads. If you think of Java, yes, Java threads are there. If you think of Python, Python also supports thread. If you think of a Go programming language, that also. So threading support is available in built-in Go. Just the thing is, they are called as a Go routines or goofers. Okay, but anyways, the concept is same. But whenever your process has multiple threads, then we need to save multiple PCs, that is program counters, in process control block. That is the requirement, because it is not single. Now, which thread is selected depends on that. You need to select the PCB for, program counter for next instruction to execute. Okay, so that is thread. Now this is how the processes are represented in Linux operating system. The structure used for that is here, task struct. Okay, and PID itself is a type. It is just unsigned integer. That is a process identifier. The state is just long. Next one is time slice. That is for scheduling information. Now this is the pointer, which points to the parent process. This is again for Linux and most of the operating system, I guess. If you have multiple processes running, then these processes are organized in hierarchical manner. So each and every process has some parent process except init process, because that is a grandparent for all. Okay. Similarly, it can have the list of children also. So there is parent process, there is list, this is list here. So this is actually linked list. This is just a pointer to parent. This is linked list. Struct file, struct star files. Yes, here you can see. This is list of open files. Now, somebody asked the question whether this PCB is fixed memory or dynamic memory. Now, if you have a look at this, you can easily calculate the size of this task struct. So even though pointers are there, yes, maybe the information is stored somewhere, but the size of PCB will be definitely fixed. Okay. And then these are okay. Looking at this diagram, can anybody mention what is the data structure represented in the diagram? So this is one PCB. This is next PCB. This is next PCB. Yes, yes, it is. No, it is not singly. It is doubly, because there is 4 pointer and back. So this is forward pointer, this is backward pointer. So it is doubly. So it is doubly linked list. Okay. And this is one pointer. Which process is currently executing? Okay. So now working is very simple. You imagine something like this process is currently executing, and now if this is waiting for something to happen, okay, scheduler will move to the next. Scheduler will check its state. If it is ready, no, it will move to the next. Is it ready? No, it will move to the next. Is it ready? Yes, schedule it. Okay, so scheduling becomes very, very simple. If the processes are organized in such a way That is the doubly linked list you can see. And doubly linked list of what? That is again important. It is doubly linked list of PCB. Always remember. It is doubly linked list of PCB. Fine. Now the next part is process scheduling. The process of scheduling is like selecting the next process for execution. And there is something called as a scheduler. It is the module in the operating system which performs the task of scheduling. So there are two definitions, scheduling and scheduler. So scheduling is the process of selecting next process for execution. And whoever performs this task is called as a scheduler. That is the scheduler. Okay. Now, the design goals for scheduler are, the scheduler is supposed to select such a process. So there are a few guidelines for that. Number one, it should maximize the CPU use. Let me give very simple example. Maximize CPU use is something like one process is waiting for some input and another process is waiting for, say, some sort of IO completion. Third process is also waiting for some sort of input, and fourth process is waiting for the processor. Now, if I want to switch, definitely I'll not switch to first, second. Reason is first, second, and even third, because first one is waiting for input, second one is waiting for IO, third is waiting for some sort of input, and fourth one is ready. It is waiting for the processor. So definitely I'll select the process which is waiting for the processor only. Because if we select a process which is waiting for completion of some sort of IO, so there is no task for the CPU. It will be just waiting. So schedulers should select the process in such a way that it should maximize the CPU use, because CPU use is directly proportional to the throughput, and throughput is like how many processes are finished in unit time. So if you maximize the use of CPU, definitely you are getting more throughput. And secondly, it should quickly switch process onto CPU for time sharing. Quickly. Now this time maybe you will not understand this. Why quickly? Because there is something called as swap device. Let me tell you about that. What is the swap device? You imagine something like whatever memory is there, it is full, and now I want to create one more process, and memory is actually full. Is it supported? Yes, that is supported by modern operating system. Now, how it is supported? What happens is whatever the suspended processes are there, whatever the waiting, suspended or waiting, whatever the waiting processes are there, these processes will be swapped out. These processes will be removed from the memory and stored on a dedicated part on hard disk. That is a swap partition. If you have installed Linux operating system, you are already aware that Linux needs one partition called as a swap, right? So that swap space is utilized as a memory. So that process is now not in memory. So removing few processes from memory onto the swap device, then there is a space to create new process. Fine. Now, for example, if scheduler select the process from swap device, then definitely that creates problem. And what is the problem? The problem is whenever you select the next process from swap device, first upon you need to take that process from disk into the main memory and then start execution. And actually reading something from disk needs more time. Disk is very slow as compared to processor. And that is the reason scheduler has to select such a process which can be quickly switched onto the CPU for sharing the time of CPU. Anyways, that will again affect the throughput. So few guidelines. The one of the tasks of scheduler is to select amongst available processes for next execution on CPU such that the switching should be quick and it should maximize the CPU use. Got it? So swap in, swap out, also called as roll in, roll out. They are also called as roll in, roll out. So that is the scheduling and the scheduler. Operating system makes use of different queues of processes. So processes are always in some sort of queue. So for example, if I say there are 10 processes waiting for the process that is with the state ready, actually there is a ready queue. Actually there is a ready queue. And these queues are managed again by the linked list as I mentioned. So different types of queues are used by operating system, like job queue, set of all processes in the system irrespective of what is the state of that process. That is a job queue. Ready queue, set of all processes residing in main memory, ready and waiting to execute. Don't get confused with this waiting word. It's not like waiting queue, because waiting queue will be again different. Device queues are there, set of processes waiting for input output device. So that is a device queue. And say for example, one process is waiting for some sort of input. So it is in say keyboard queue, because keyboard is also a device. And now once that got some sort of input, now that becomes ready. So the process which was previously on device queue now becomes ready queue. So that means processes are actually migrating among these various queues. We saw the state transition diagram. So depending upon state, there are different queues. Fine. So now the task of scheduler becomes very simple. It will just select the process from the ready, because ready queue holds all the processes. They are already in the memory and they are ready for execution. They are just waiting for the CPU. So scheduler don't need to look for all the processes. So job queue is not at all need to be consulted by scheduler. Okay. This is the example. So for example, ready queue. These are all queue headers. Head is pointing here. So PCB7 is there in the ready queue. It is pointing to PCB2, and this is end of list. Now this is which data structure? Yes, singly linked list. That is a singly linked list. Okay. Okay, have a look for the poll. By mistake, I given more time. No problem. You go on this. Till then, okay. So we'll continue here. So this is the magnetic tape unit 0. So this is one of the device. So this is one device, magnetic tape unit 0. It is empty. That means nobody is waiting for it. Nobody is waiting for it. Out of 110 participants, 85 are present, I guess. 86. 86. Yes, that is the final thing. Fine. So this is for magnetic tape unit 0. No process is waiting for that. So this linked list is empty. Look for this magnetic tape 1. Yes. That means even though we have multiple units of any specific IO device, we have a separate list for that, separate queue for that rather. Now disk unit 0, there are 1, 2, 3. Process number 3, process number 14, and process number 6 are waiting for this disk IO. Okay. Terminal, yes, PCB 5 is waiting for the terminal. So these are all device queues. This is ready queue. Similarly, maybe we have a waiting queue. There is job queue. So operating system maintains multiple queues, and most of the queues are implemented as a linked list. Maybe singly linked list, maybe doubly linked list. Here, all singly linked lists are maintained for different queues. Okay. Now you have a look at this queuing diagram, which represents different queues, resources, and flows. Now, a process which is in ready queue, you can think of any process P I. Think of any process Pi which is in ready queue, selected by scheduler. Once selected, it will move here. So now it is running. If it is running, then maybe waiting for some IO, it will follow this path. That will be added to IO request queue. Once that IO is finished, once this IO is finished, it will move to ready queue. Here, again selected by the scheduler, again running there. If it is a time share system, then let me select another color. If time quantum is finished, process will move from CPU to time slice expired. Okay, from time slice expired, again it is not waiting for anything, so it will move to ready queue. Selected by the scheduler, executing. Suppose it is that process is creating another process, making use of this fork. Child executes, it goes back to ready queue, same thing. It is waiting for some sort of interrupt, some event to happen. Then from CPU, it will move to here. If interrupt occurs, that is finished, then again it moves to ready queue. If the process finished its working, it will move to exit. So that is the way the process is migrating from one queue to another queue depending upon its dynamics. Okay. So somebody is saying, sir, I am not able to give the poll from start. It says presenter has not opened the poll. I guess you become late there because poll was open for 1 minute and 85 students have already given. And there is no such settings there where I can restrict any particular student on giving the poll. Maybe network connectivity issues are there. Anyways, now that poll is already closed. Now you can do anything. Even I can do anything. So fine. So let us stop here.